Hello, everyone. My name is Sébastien Blachère, and I work for SKF in the Research and Technology Development Center in the Netherlands. And the webinar of today will be on bearing life statistics. The objective is not to go too deep in the statistics, but more to explain some of the key notions behind the reliability of bearings, like the L10, for instance. The bearing life statistics is essentially supported by the 5 pillars that you can see here in the 5 pictures. So namely the physical modeling of life, the life testing, the statistical analysis of life data, and of course the understanding of the surface and subsurface failure mechanisms. The webinar will have 4 parts. We'll first start with some basic notions of statistics that are needed to understand the statement on bearing life. Then we will go into the specific statistical distribution, the Weibull one, which is the one used for bearing life, and its key parameter, the L10, that is used to rate the life of bearing and select bearing sizes. Then I will go on a specific topic, the higher reliability levels like L5, L1, or L0.01, or whatever. This is a special topic for which I would like to draw the attention on the do's and don'ts there. And finally, I will discuss a key topic, which is life testing, because whatever you develop around bearing life in terms of modeling, you always need to go to life testing to get the truth and be able to prove for self and towards our customer that whatever has been developed and modeled is indeed valid experimentally. All the notions that will be presented are used also in the SKF bearing catalog, but I will give you some more flavor a bit behind the screen to understand better these notions. But let's start with a nice quote from Bertrand Russell saying that probability is the most important concept in modern science, especially as nobody has the slightest notion of what it means. And indeed, it is quite easy to misunderstand a statistical statement, or even to be fooled by a statistical statement. And that's why it's very important, I think, to have some notions to be able to have a critical eye when we are facing such statements. So, talking about statistics means that we are looking at a phenomenon that encounters variations, and variations can also be called randomness. This applies to many phenomena, like, for instance, human life. And when you have such variation, you cannot make statement about a deterministic value. Like, for instance, for human life, you cannot say that the human life is 60 years. It has no sense. You have to describe this phenomenon, in that case, the human life, in a statistical way. For instance, you can say that for Western Europe, life is less than 6 years for 10% of the population. This is a valid statement, and this is a statistical statement. The variations that are causing this spread in the phenomenon that you are looking at can be of various sources, like external, lifestyle, climate, or food, or internal, like genetic. And the same more or less holds for bearings. Once you have these variations and you have observed them, you need to go further to model this variation. And the way to do that is to use a statistical distribution. The most well-known statistical distribution is the Gaussian or normal distribution, but you have a full zoology of distribution that you can use. And a statistical distribution, corresponds to a function called the cumulative distribution function that is defined as presented here as a function where for a value x, it associates the probability that the life is less than X. So for instance, for life, if X is 60, then the output, the probability of life being less than 60 years will be 10% or 0.1, depending on the way you define the probability. So the next step, once you have chosen your statistical distribution, is to estimate or assume the parameters, because every statistical distribution comes with it's a family of distribution, and this family is fully determined by the value of these parameters. So every every statistical distribution has one or more parameters to be determined. For instance, for the normal or Gaussian distribution, there are two parameters, the mean and the standard deviation. For the one of interest for us, for the Bering life, the Weibull distribution, we also have two parameters called the scale, and often denoted eta, and the shape parameter beta. For the scale parameter, we can also use directly another parameter, the L10, which is the key one for Bering life. And at the bottom, you have the full formula for the Weibull distribution, either with the parameters eta and beta, or with the parameters L10 and beta. Even if L10 is the main one, I would like to say a few words on the other parameter, the shape one, beta. This parameter, it's not directly linked to the life as L10, but it has an influence because it measures the dispersion or the spread of the data. For instance, if you have a high beta, it means that you have a high concentration. In other words, it means that if all the failure times will be rather close to each other. And for low beta, then you have a high dispersion, and in that case, the failure times corresponding to the life that you want to model, these failure times will be very different from each other. When beta is larger than 1, then this, we call it the aging process, meaning that the old are less reliable than the new. This is the case for bearings, although for bearings, beta is usually just slightly above 1. For beta equal 1, this is the memoryless, meaning that the old are as reliable as the new. And for the beta equal 1 is used for certain industry, like for instance, computer chip. And beta less than 1 corresponds to the infant mortality, when the old are more reliable than the new. So that's it for the beta, but I think it's important to spend a few minutes on that. Now let's go to the core parameter, the L10. So we saw that for human life, we had various factors that are creating these variations. It's the same for Bering life. And as you can see in these green bubbles, you can have a lot of different factors like speed, contamination, load, etc., that are influencing the Bering life. And this influence can be captured by the life model, in the sense that we are able to quantify the influence of, for instance, the speed on the Bering life or the load on the Bering life. But beyond these parameters, we have also extra factors that will create further variations that will cause even variations from individual to individual. So even if you have a population of bearings that are running under the same speed, the same contamination level, same load, etc., then you will always see variations in life, because there are other factors that cannot be fully captured, and these other factors will still create variation. For instance, it could be the inclusion size and the location of those inclusions in the steel, the surface roughness, or the clearance. Once you have this variation, you still need to quantify something, and the key parameter for the Bering life is this L10. And it's very important to fully understand the definition of this L10. This L10 is just what is called a life percentile. So the definition is just a value x, such that the probability that the life is less than x is 10%, or that 10% of large population will fail before L10. Here, the keyword is large, because this statement is only valid for large population. For instance, if you take 10 bearings, it's not true that systematically one bearing will fail before the L10 and the other 9 will fail after the L10. You need a large population to make this statement with 10%. Another way to see the L10 is to say that it's value x, such that the probability that the life exceed x is 90%. So it's really similar. And this L10 is really the typical life percentile that is used for bearing performance. And it can be represented like here on the plot of the cumulative distribution function. Another life percentile that is of interest is the L50. It can be defined in the same way, except that instead of being the 10th percentile, it's the 50th percentile. So the L50 is a value y, such that the probability of the life, of having the life less than y, is 50%, or equivalently, value y, such that the probability that the life exceed y is 50%. This L50 is called the median life, and yes, it's important to understand that this is different from the average or the mean life. And DL50 is also used for reliability, for instance, for grease. So once we know the definition of DL10, we can now go further into the entire Weibull distribution. And as I mentioned before, the distribution is defined by this cumulative distribution function. A simpler way to draw and to plot this function is to use a Weibull plot, where the axes are made such that a fit with the Weibull distribution correspond to a straight line. Doing so, it's very easy if a set of data is fitting well with a Weibull distribution assumption, because we only need to see if the data plotted on this special Weibull plot are well aligned or not. And for a long time, it has been assumed and proven that bearing life are following such a Weibull distribution, at least for most of its lifespan. And actually, this phenomenon, this Weibull distribution, is valid for a lot of application where the failure mechanism corresponds to a weakest link approach. So when you have a sequence of subsystems where a failure comes from one among these subsystems. And once you have plotted this data and marked the L10, you can see what I mentioned before, that 10% of this population will fail before the L10 and 90% after the L10. This is valid because here, in that case, we have really a lot of points, a lot of experiment. So we have a large population. And one thing that is extremely important to remark on this plot is the very high factor, multiplicative factor that you see between the first failure and the last failure. It's above 100, and this is typical for bearing life. What does it mean? It means that you have a wide spread of failure times. Even if the whole population of bearing are under the same operating conditions. And this is what I meant before with this low beta, so beta close to 1. And this is very important to keep this in mind, because whenever you know the L10 value, you always have to remember that an individual failure can easily occur much before the L10 or much later than the L10. This is not in contradiction with the value that you have calculated. It's just due to the natural spread of life in available distribution. So this L10, it's obviously we need live models to compute this L10 and to give a rating from it. We have SKF various models that are taking into account different type of inputs. We have the basic one with essentially the capacity and the load, the SKF rating life, which is taking into account more inputs from the one that I presented before. All of them are integrated in the SKF Bearing Select, but we also have more advanced engineering software like SKF Simpro Quick and SKF Simpro Expert that are available to give advanced life calculations. And recently, a new model has been developed and released. It's called GBLM, for Generalized Bearing Life Model. If you need more information about this model, there is an evolution article available online. The reference is there. But just to give you a flavor, this model, the GBLM model, the specificity of this model is that it differentiates failure mechanisms coming from the surface from failure mechanisms coming from the subsurface. And doing so, it can be more precise in some very demanding operating condition or on the influence of some specific design features. And this model was actually released last year successfully for hybrid bearings. So it's bearings with ceramic rolling element. And from this model, there's another benefit, which is the relative surface fatigue. It's an index between 0 and 1 that measures the predominance of the surface failure over the subsurface failures. And if you have a low RSF close to 0, it means that you are in the classical subsurface fatigue phenomenon. When if you have a high RSS close to 1, then it means that the surface fatigue will be dominant. It's not to say that something is good or something is bad. It's more to know in advance what is more at risk between the surface and the subsurface, so that you can, in the field, apply some mitigation action to prevent the failure to occur. Another topic linked to the life is the system life. So a system is composed by a certain amount of bearings, like for instance, you can think of a gearbox. And when you have such a system, you need, of course, to estimate the life of the system, called the system life, from the life of the individual bearings. And if you apply basic calculation to do this, to calculate the L10 of the system, you see, like in this plot, that you have a very steep decrease of the life as a function of the number of bearings in your system. This conservative basic calculation can be improved, but only with some very specific study on the system itself, like for instance, doing a failure mode effect and analysis, FMEA, where you can understand and also quantify the dependency between the different bearings, and therefore you can have a more accurate calculation of the life of the whole system. The last point from the life is the case of variable conditions, because the life models that I presented before are giving you a rating, an L10 life rating for specific conditions. But in many applications, the conditions are not stable over time. You may have, like in this case, an alternation between a light load, heavy load, light load, etc., etc. So in that case, you can also compute the life over time with these specific load cycles. The first step is to compute the life for the different condition, in this case, the light load and the heavy load, and then to combine them with this formula, which corresponds to a geometrical average. And this formula will give you the life of your application with some weight factor depending on the time share between the different operating conditions. But from this formula, and in this case for the variable conditions, it's very important to understand that because of the nature of the geometrical average, the short life, so the life from the toughest condition, like in this case the high load, will influence more the resulting life than in the normal linear average. So it means that if we have such condition, it's very important to have a good estimation, especially of the short life, the life for the toughest condition, and especially if you encounter like peak load, you have to be very careful on the value and the time share for this load. But of course, this is valid if you have some peak load, but not too high, because it should not create immediate damage on the bearing, like for instance plastification. The next topic that I mentioned in the overview is the high reliability level. We already saw that the definition of the L10, so L10 is the life that 90% of a large population will survive. In a similar way, we can define other reliability levels like the L5, the life that 95% of a large population will survive, and so on, and even L0.01, the life that 99.99% of a large population will survive. This is possible, but if we go back to the initial example of the human life, like for Western Europe, as I said before, the L10 is about 60 years, but the L1 is about 15 years. And it's quite straightforward to realize that the reason why someone is passing away before the age of 15 is essentially different from what is happening around 60 years. Therefore, the correlation is very limited between the L1 and the L10. And this is something important to keep in mind, because if we ask ourselves whether from a technical point of view, we can extend the life estimation to a higher reliability level. So for instance, we know the L10 from life models that have been computed, modeled, and calibrated. Can we extend this reliability level to a higher one, like the L1, for instance, corresponding to the life reached by 99% of the population? In theory, yes, it's always possible. You just need to apply the math. But in practically, it's quite hazardous to do that. First of all, because of the issue that I just mentioned for the human life, and that could also apply for bearing lives, that you have the risk that at this high reliability level, you are in a range of time where a very different failure mode is occurring, and therefore the correlation is not there to allow this extrapolation. The other reason is that the Weibull model, although it fits very well with with most of the lifespan of a bearing, it has some limited validity, and typically it is assumed that the validity comes between L5 and L60. So if you start going below the L5, so towards the L1 or even further, then you may go outside of the range of validity for this assumption of a Weibull distribution. Nevertheless, in the ISO and in the SKF catalog, you have this life adjustment factor A1 that is there to extend the life from L10 to other reliability level, but this factor has to be used with very good care, and especially it is not allowed to use it for advanced fatigue calculation, because these advanced fatigue life models, they have a high level of precision in the life estimation, and applying this factor will alter this precision. This issue that I just mentioned can also be illustrated when several tests are pooled in order to get enough statistics to have some information about this high reliability level. And in these three graphs here, although you have very few points towards this reliability range, like around the L1, L2, you clearly see that we have different behavior. The middle one seems to fit well with the Weibull line, but the left and the right one start to deviate, and also from different sides. So once again, be very careful with this extrapolation to higher reliability levels. The next topic is about live testing. As I mentioned at the beginning, whatever is developed in terms of live modeling, everything needs to be proven by an experiment done with the live testing. So we need to run this test to prove or to disprove whatever has been calculated theoretically. And because the life of the bearing is as this wide dispersion that we saw before, we need to test a lot of bearings, because if you just rely on a few tests, then you will face the risk of not being sharp on the L10 estimation, because you may have the chance to get late failures or to get early failures, and this will bias your results. And the objective of the live testing is really to get a precise and an accurate estimation of the L10. Therefore, you have to choose the test strategy in a very careful way. There are many challenges in live testing. The first one is to have a very well controlled environment. Why? It's because the life model is giving the life for specific operating conditions, as we saw before. So we need the full sample, so all the bearings used for a single test, we need them to run exactly under the same conditions. And therefore, we need this very accurate control system. You also need to monitor everything. Everything from the bearing, as I will mention later, from the vibration, the speed, the load, etc. You also need to carefully choose your samples. So the sampling stage is really key. And of course, the test strategy has to be defined in a way that you will be almost sure to get a precise estimation of the L10, but also you have to optimize the occupancy of the test rig to allow as much live test as possible. And the last challenging point is the flexibility, because these test rigs they need to be used for different bearing types, and they need to be used in different operating conditions to help the development and the validation of the different models. So one key point from live testing is the condition monitoring. So a lot of parameters can and are monitored, like the load, speed, temperature, vibrations, oil flow, or the power consumption of the motor. And a lot of improvement has been done in the past years on that point to get very high resolution in this recording, storing, and analysis. And this is not only important in the test itself to understand the behavior of the bearing. It's also important for the development of the sensors that will be also used in the field, and also on the analysis of this data that will be used also from field data run analysis on this data, and in the future to get more predictive algorithm to be applied in the field. Once the test is over, then you get failure times and suspension times. So suspension times means that the test has been stopped, but the bearing has not failed. From this data, you need to estimate DL10, and to that purpose, we have an internal tool called Weibull that has been designed to get the optimal precision on the key bearing parameter, which is the DL10. The live testing is much more than just a sequence of tests, because over the years, doing this test, you really build up a huge database of key information about the performance of the bearing in various conditions with different bearing type, etc., etc. And this is key because you every time you develop something new, a new steel, a new design, etc., you have this database that can serve as reference or baseline to compare with. And so doing this comparison is really essential. And to do this comparison, one thing that is extremely important is to have a very precise estimation of DL10. And this precision is captured by these intervals that I'm pointing out at now, this red horizontal interval there for the red part for variant B and the blue part for variant A. These intervals are measuring the precision, or if you want, the uncertainty around the L10 estimation. And to get a good comparison between two variants, you really need these intervals not to overlap. And in the right figure here, you see a huge overlap, and which means that although the blue variant here seems to perform a little bit better than the red one, you cannot make a full statistical conclusion out of this test because of this huge overlap. So in the test strategy and the number of bearings is of course helping you to get a higher precision and therefore a shorter or narrower interval. It's a bit like, for instance, if you measure the height of two persons in Paris and get an average height of 1 meter 80, and you do the same in Amsterdam and get 1 meter 75, then of course you will not conclude that people in Paris are taller than people in Amsterdam. First of all, because it's the opposite, and secondly, because you only tested two persons, so your test is very poor, and therefore even if you could make an average on both tests and do a comparison, your comparison is not valid because you don't have a good precision. You have a huge uncertainty on your conclusion, and therefore you cannot do a really trustful conclusion out of that. So to conclude this presentation, I just want to recap 4 key messages that I made during this webinar. The first one is the definition of DL10, so that 10% of a large population will fail before DL10. And here I insist on the fact that large is the key word there. So it's really important to keep this definition in mind. The second one is that the bearing life has a very wide spread, as we saw in the plot, and as the plot is also here. And this is really important because, as I mentioned before, even if you know DL10, you will have failure times that are much earlier than this and much later than this value. And this is not in contradiction with the value of DL10. This is just the natural spread of life of a bearing. The third point is about this high reliability level, like L1, L0.1, etc. This is always theoretically possible, but in general, it is quite hazardous to make this extrapolation unless this extrapolation is backed up with some experimental or some field data that will indeed show the validity of this extrapolation. And the last point is about live testing, because this is really an essential step to assess bearing life. And this is a very challenging one, which needs a high level of equipment, very experienced team, and tuned test strategy to accomplish the task to get a good L10 estimation out of the test. Thank you for your attention,